Hello, and welcome to this session on the future of HPC. My name is Jan Fischer. I'm the global evangelist at Red Hat, responsible for our HPC strategy and emerging technologies that are coming with exascale computing. Today, I'd like to talk to you about moving traditional HPC to scalable containerized infrastructure. Let's look at the agenda. I'd like to cover a couple of trends that we're seeing in HPC today. We will cover 3 phases of adoption that we see in containerized technologies in HPC. And I'll share some tools that will simplify large-scale container deployments. And at the end, we'll talk about success stories and customer references. With that, let's get started. Emerging technology trends in the past 2 or 3 decades have been very telling. The advancements in the off-the-shelf general purpose computing have led to a dramatic growth of the sector from 2 billion to about 28 billion, and has really contributed to the fact that number of systems deployed every year has grown exponentially from hundreds to hundreds of thousands. This really was driven by the fact that the hardware has become more ubiquitous and more accessible to people, but also by the fact that open source software, Linux in particular, and the associated software stack has essentially grown in popularity and has become the de facto standard for these supercomputers. So the entire segment has grown, has become more affordable, has been democratized in a way by the advent of the off-the-shelf hardware and open source software. Let's look at the immediately accessible emerging trends here. This is what we're tracking today. And HPC keeps evolving, which is an amazing thing that many people have not foreseen 30 or 40 years ago when HPC has been just started. Today, the traditional HPC has grown to be more of a cloud and enterprise player. And vice versa, the enterprise customers have looked to HPC to help them solve some of the most challenging problems. So let's look at that. In 2020, Hyperion has performed some studies, and Hyperion is probably the most prominent analyst research company covering the HPC sector. So what their study showed is that the cloud adoption across different HPC sites has grown dramatically. About 67% of sites reported running some HPC jobs on premise, but nearly a third, about 29%, have actually running some of these jobs in public clouds. Running HPC in the public clouds have really been running HPC in clouds has a broad impact on the entire sector, as that becomes a viable option for many HPC workloads. We've seen adoption of the cloud. Clouds are naturally very heterogeneous. We're now seeing advancements of different architectures, as in ISA, instruction set architectures, into HPC and also into the clouds. So Intel has historically maintained the lead with 63% of all the HPC sites. And AMD, while gaining market share on Intel, they really have the predominant architecture for the entire set of HPC sites. ARM is the newcomer in this space, but with Fugaku and really shining at the top of the top 500 list, I think ARM has established itself as a pretty strong contender. So we're watching that space very closely. In IBM Power, with the two systems that have been at the top of the list, top 500 list for a while, is obviously an interesting kind of incumbent player in the space. But what it tells us, really, the fact that different architectures are starting to show up, is that the x86 systems have really been bumping against the limit and reached their ability to serve the demanding and variously kind of interchangeable workloads that are coming into the light at HPC sites in the last few years, in the past few years. This has grown and given kind of a push to the ascent of accelerators. So accelerators now are a really big part of pretty much every single system that exists on the top 500 list, with a very small exception. And NVIDIA has about 62%, according to this research, of the accelerators in forms of GPUs. AMD and Intel discrete graphics are also in the play in the single digits, with FPGAs and AI accelerators trailing far behind. But the advent of these accelerators and their kind of position now within the market tells us that we will see more and more of these in the coming days and the coming years. The other part that really has disrupted the industry for both enterprise, high-tech industry for both enterprises and HPC users is the advent of containers and containerization in general. So containers have arrived to help really to localize and to create an isolation layer for the applications, with the ability to package and ship your applications across sites and relatively easily combine everything that you need, your application requirements and your data together in a nice package, and be able to share and ship it elsewhere. So in the Hyperion study, about 36% of respondents actually use high-performance computing, HPC infrastructure, in the enterprise data centers to accelerate business operations, which means that they are running containers in there. And they definitely running containers when we touch the machine learning and deep learning. Those workflows are dependent on containerization and really have been the pioneering technologies for the container adoption. But with the convergence of these enterprise stacks and HPC, we're seeing the kind of cross-pollination of the technologies happening, and the container adoption in HPC is also starting to grow, right? So while the sites, the enterprises use containers for predominantly data-intensive machine learning and deep learning workloads, and they're running simulations, analytics, in FSI space, financial services with fraud and anomaly detection. They're running some business intelligence, some marketing applications, et cetera, et cetera. What we're seeing even today on the HPC side, actually over half of the top 500 supercomputers in the world are no longer just pure HPC systems. They are coming as a part of the different verticals: telecom vertical, social networking, gaming. We've seen oil and gas companies at the top 10 very recently. So we're seeing all of the trends that tells us HPC has gained momentum in the enterprises, and the enterprise technologies, such as containers, are bleeding into the HPC. Keep that in mind as we go through the slides. So what the future of HPC looks like, given the trends that we just looked at? I think that everyone will agree that driven by machine learning and deep learning, HPC technologies are moving into the enterprise. And since the machine learning and deep learning require accelerations, enterprise applications will be taking advantage of it. And as a result, we will see more and more HPC infrastructure, as in the ability and the architectures that they use in HPC and the ability to run things at scale, bleed back into the enterprises in the bigger entities like large banks and big oil and gas companies. In the same time, we see a convergence of cloud usage in HPC. So large HPC sites rival big clouds, but with all of the infrastructure on-prem running directly in the data center. But hyperscalers are also looking for the technologies that have been used for years in HPC and leveraging them. They also pay more attention to accommodating customers that want to run HPC workloads in the cloud and changing and adopting the infrastructure to support those customers with the HPC workloads. And like I said before, HPC is increasingly using enterprise technologies as well. Containers is a great example. Data analytics is the other one, and CI/CD and DevOps has been really on top of mind for some of the HPC sites as they're trying to streamline the development of and kind of validation of their applications and their workloads internally. So now that you're familiar with the current trends and how the future of HPC is evolving, I'd like to focus on one area that serves as a common thread across all these three topics. And that is the containerization. So let's talk about containers and containerization of the high-performance computing. We outlined three phases of adopting container technologies in HPC. We did that about 3 years ago, and I'd like to discuss them with you. But before we do that, let's talk about infrastructure and applications as two different domains for which containers are designed and can be used. So when you ask what are the containers in general, it really depends on whom you're asking, because for application developers, it's an ability to package applications with all the dependencies and ship them around and deploy in any environment, practically any environment, within seconds. It's very easy to deploy and access and share, as well as, they're lightweight, so it's easier to ship them around. If you talk to the infrastructure people, containers also represent a fascinating technology, right? Because they are simpler, lighter to run than the virtual machines, and they have a smaller footprint in the data center. They consume fewer resources, yet they provide a pretty good degree of abstraction and also kind of isolation, workload isolation. On top of that, they are portable across different environments. So having said that, and keeping in mind that we'll probably be talking more about the infrastructure value of containers, we also will touch on the application side of it as well, because there are benefits for HPC users to in a similar way as they are for the enterprise developers to use containers for shipping and distributing their applications. But in general, the adoption of containers can be put into these three different or distinct phases, right? So back in 2019, Red Hat adopted this multi-phase approach to containerization of HPC. And we outlined the three criteria that you see on your screen. Enabling single host environments, where you could run containers on a single machine, whether it's your laptop or a server, but you can run them natively just using the container runtime that exists on your system without having to use any large-scale orchestration mechanisms. The second phase is, that needs to happen is the scale of the HPC workflows needs to be adopted to run in containers, right? So not just to scale them, but also just to make them available in containers. And the final phase is the orchestration of large HPC jobs using orchestration engines such as Kubernetes. So let's deep dive into each of these phases as we go through this presentation. So the first phase that we saw a lot of sites go through, and some of them are still going, is to enable single host environments. This is really all about education. This is about explaining to the developers, explaining to users why they would want to change their tools, why they would want to change their usage patterns. Education is very important. It also takes time, and we really thought that having the set of user-friendly Linux native container tools that I'll talk to in a minute, on the next slide, is extremely, extremely important for making this journey and making the kind of development experience very friendly and very useful. We also have thought of the fact that developers often want to share the work with the world and share their applications or share their containers outside of their immediate organization, of their immediate environment, et cetera, et cetera. And we thought that having a universal base image to build containers that allow you to distribute those containers freely would be extremely useful. And I'll talk about that as well. But let's first talk about the container tools, right? So containers have been really brought back by Docker as a company a while ago, and they were focusing really on the enterprise developers. They have come up with the certain design that wasn't really compatible with the requirements of the HPC from various standpoints. First and foremost was probably the security. So Open Container Initiative was created to essentially help steer community standards around containers. And under that umbrella, Red Hat created 3 projects that are fundamentally important for HPC. First of all, we created Podman. Podman is the runtime that can live on your operating system environments, such as Red Hat Enterprise Linux. It could deploy containers. It uses a very familiar syntax to Docker. It really keystroke for keystroke, command for command, backwards compatible with Docker. But it is a very secure, different environment that allows you to run your HPC jobs without having to worry about root access and other specific requirements that may be not as important in the enterprises, but extremely important in large HPC sites. So we all kind of backed the Podman as a runtime, but we also created a set of tools to allow you to look inside the containers, inspect and audit the content there within the container image, and also to create those images, right? Build something that, or modify something that you create on the fly, and an ability to kind of compose the content of the container directly. And for doing that, as I mentioned before, we thought it would be a good idea to have a base image or an operating system compatible based image that could be taken to any site anywhere in the world and run as a container, running on any non-Red Hat technologies as an unsupported but freely distributable container. And if someone decides to have a support for that container in the environment and they happen to run Red Hat there, whether it's a Red Hat Openshift or Red Hat Enterprise Linux, all they have to do with a click of a button is to turn on the support subscription, and they would be covered. Not only the environment, but the container that they created or that was just sent to them. So this was really done to enable the development, and also extremely important for the sharing and scientific advancement of the scientific research that is very important in many of the high performance computing sites. So you can take the UBI image, you can share it with your colleague. The colleague doesn't need to worry about anything that they don't have to worry about, providing subscriptions or having to pay for it. It's really just to be able to distribute this images freely in the containers freely. So these are the tools that Red Hat put together to simplify the deployment of the containers on a single host and in the environments that essentially tailor to the developers. Because you can say that this could be done, like I mentioned before, on a laptop or desktop or on a server in isolation. But then we get to the second phase, which is a work phase. And this is where we really see the requirements coming from HPC sites to scale this workload. Once the container is developed, you want to do something with it, right? There is a reason why you build a container in a portable way, so you want to deploy it, right? You want to run it in other places, you want to share it, etc., right? And you probably would want to run that at scale. So how do we get from here to there, from single host to a multi-host to a cluster environment? Well, I think we all know that if you can manage one host, then you can manage multiple. You just need management interfaces, and you need provisioning to move these containers around. And that's really what the middle phase or hybrid phase is, between a single host and really running on a fully orchestrated model. Sites have invested a lot of time and money into the existing workflows that use the schedulers that they like. Pick your choice there. There's so many of them, most popular being LSF and maybe Slurm and a couple of others. But the idea here is that you really have now the chance to run your containers with the existing tools, existing schedulers, right, on individual hosts within a cluster. So this would be kind of running a batch job with the scheduler, but running it in containers. That's a very fundamental next step for many sites as they looking and changing the kind of their view on how to run large jobs on this big clusters, and potentially exascale systems that as they starting to arrive. The other part of it is, historically for containers, having direct access to hardware was not extremely important, and that's where we start looking at enabling features like access to accelerators, GPUs, NICs, essentially very essential hardware features into basically from the container right into the hardware. And I'll talk a little bit more about that. And finally, like I said, these batch jobs run MPI, message passing interface. They really depended on having that, and container is not natively enabled to run that. So we saw that as a gap and also started to experiment with that. So here's an example of what you may need to do in order to enable containers to actually see specific hardware resources. In this case, it's GPU, right? and the container runtime is Openshift. But it also could be Podman, for instance, right? Any container runtime. But for the Openshift, we have an interesting capability called operators, and that operator net framework that we have allows you to build operators to simplify certain tasks. So here we have NFD operator. It stands for Node Feature Discovery operator, poking around on the hardware and finding the fact that there are GPUs present on the host and labeling those hosts, those nodes to be GPU capable. That information propagates into the overall cluster on Openshift. And when the workload comes in, it now will be mapped, and it has a request for using GPU acceleration. It now will be mapped to those nodes that have indeed access to the GPUs, right? And the special resource operator actually takes care of mapping the GPU enabled nodes to the applications or to the containers that are requesting them, right? So that's one of the examples where the need for direct access to hardware kind of dictated a creation of a certain class of operators to enable that. This is something that Red Hat has been tracking and doing routinely. The other one was the message passing interface, as I mentioned. What you see on your screen, I don't know if you can see it very well, but it's essentially an instruction manual on how to enable Podman to run with MPI. And that's really gives you an idea on how you can deploy a workload in multiple containers using the standard MPI, OpenMPI interface. That's specific to Red Hat Enterprise Linux RHEL 8, for instance, right? But that's another feature that you can't really function without it if you really want to run at scale. So that tells you, the level of investment that we have been making or have made so far into the enablement of the containers. And now, admittedly, we're all entering this last phase, the run phase, where we orchestrate HPC jobs with Kubernetes. And Kubernetes implementations are out there. There's multiple different flavors that you can see or find. We have the one that's called Openshift, and I'll talk about it in a few seconds. But the main idea there is to create an ability for the MPI schedulers to coexist and potentially work in parallel or in concert with the Kubernetes. So Kubernetes has its own scheduler. Let's call it a primary scheduler. So if we want to make the HPC jobs to be more aligned with the resources that we have, sometimes we don't want to go to the primary scheduler, or sometimes it doesn't know what to do with certain resources. So we could use an interface, standard interface, to integrate your choice of the scheduler, let's say like Slurm, into the Kubernetes, and Kubernetes will know to pass certain tasks and jobs off to that scheduler to operate on the pods that Kubernetes doesn't have information or doesn't know what to do with, right? So this really gives you an ability to run a very traditional HPC job and the new HPC job that could be, containerized fully and designed to run with Kubernetes side by side. And that's a big advantage of kind of having the environment where you don't have to completely, forklift your existing scripts, your existing jobs that you design and ran in the past. So you can still do it, but take advantage of the cloud infrastructure and the interfaces that Kubernetes provides. So that's the real advantage. And, it could be run on a machine within your HPC data center or on the cloud, and it's going to look exactly the same. It's going to act exactly the same. The second part of this major shift in the phase that we entering right now is the ability to access data. So containers were not designed initially to have persistent storage. They actually, very short-lived. They come up, they perform certain tasks, they may act on the data, but they very seldom concerned with, or the applications that run, and they're very seldom concerned with saving data, storing it for long-term usage. Well, for HPC and some other enterprise segments, right, having access to data and having the ability to act on data is extremely important. So for highly parallel data access and file system access, we needed to provide the interfaces for distributed file systems so that we can integrate containers into the existing environments. I don't have to tell you, you all know that HPC sites live and die by their storage, file system storage. None of the supercomputers will exist and function without a large storage array that associated with it, or a distributed file system that lives next to it. So that's an important fact that we're working on, and I'll talk a little bit more about that. And finally here, what we're seeing, and I've talked a little bit already about, is the ability to expand the workloads into other HPC-friendly verticals. So this is the convergence of the traditional HPC with the enterprise HPC as we know it, coming from financial services, pharmaceutical, oil and gas, manufacturing, et cetera, et cetera. So this is very important. And as that cross-pollination continues to happen, we will see benefits on both sides, for the enterprises and the HPC sites and companies alike. So you may want to ask me at this point, what is going on with Kubernetes adoption and who is running HPC workloads with Kubernetes? Well, these are the types of the companies and the verticals that are involved very actively in running Kubernetes today. They're running HPC-like workloads for sure, and they're doing it at a pretty large scale, albeit most of it is still experimental. And I will talk a little bit more about who is there pioneering kind of the way. But telco providers, health and life science organizations, manufacturing, obviously financial services, in fintech in particular, oil and gas and energy sector, as well as the public sector and the largest labs. These are the main users of the Kubernetes for HPC infrastructure. So I mentioned before, Kubernetes is kind of the upstream project, and we have our own implementation of Kubernetes. It's called Openshift. If you don't know about it, this is not the session where I have time to share all the details, but please look it up. If you heard about it, then let me highlight the fact as to why Openshift exists and why is it important. For many other segments, not just HPC, Kubernetes has been an interesting technology, a new technology that comes in and does kind of disrupt the way the traditional software is developed, distributed, and actually run within the data centers, right? Openshift takes it a step further. It has more features. It has more enterprise-friendly features that Red Hat's been implementing and then putting it back in the open source community, along the lines with everything else that we do in terms of our software development. So we have been developing features in Openshift for enterprises that are really benefiting HPC customers and vice versa. And we can maybe go deeper into some of this in the next slide or two. But things like enabling the direct hardware access, which is very important for HPC sites. It's also important for some of the HPC-like environments in the enterprises. So in NVMe, SROV, access to the accelerators that I mentioned before, right? This is very important to telco and FSI, for instance. Then we are able to manage the high container-based utilization. So we're paying attention to high container content within the system and how these different pods perform and interact, right? We also focusing on the fact that in the container, the applications sometimes require the most performance, and they need to have access to the devices like I was talking before, right? So this focus on performance sensitivity and performance overall gives us kind of a very unique advantage in the sea of different Kubernetes implementations, right? Red Hat is known for providing strong, well-performing kind of solutions, software solutions, right? We're also focusing on having a consolidated platform, and this has really paid off in the past, right? Where we offer both orchestration, storage, networking features as one, so you don't have to go and piecemeal it together. And we're now starting to offer this consolidated platform for managing not just containers, but also virtual machines in the container, as well as some serverless workloads. While this may not be of immediate interest to HPC, these are the features that we've heard from our enterprise customers is important. And, interchangeable use of containers and VMs through the same management pane of glass, same pane of glass management is extremely important. But we also know that HPC sites, for instance, deploy in bare metal. How do we deploy a container platform, orchestration platform like Openshift or Kubernetes on bare metal? Well, we build a specific installer provision infrastructure implementation that I'm going to talk about in the next slide, just for the bare metal deployments. And finally, having to adopt containers on bare metal actually helps you to reduce the cost and complexity, because you don't need to have a virtualization layer on top of your hardware in order to deploy container platform. So let's talk a little bit about the full stack automation installation that we have on bare metal. So bare metal management that we kind of concern was here is built on the Metal Cube for containers and OpenStack Ironic for the virtual machines. We also have been concerned with how to manage the host power using standard industry interfaces like Redfish, IPMI, ILO, etc. We also have been concerned with provisioning installation or virtual media or PXE. So this is, if you follow the Linux, this is exactly the same problems that we had to solve back in the day for Linux. We're just solving the same problems now for containers, because it's extremely important for these containers to be treated as first class citizens on these bare metal clusters, right? And we definitely concerned with having a disconnected installation, so we created a feature that will allow you to build your own registry and do these installations remotely. But overall, I've been asked about specific features, relevant features for HPC that exist in the Openshift, and I wanted to share this. There's a full list, and we don't have the time to go in there in greater detail, but I want to highlight the fact that we talked about these categories before, right? So, you have the operator framework that I mentioned, this persistent storage, and the ability to run distributed file systems in conjunction with containers. So we have the features there. We also have the networking with Multis and HA proxy, the ability to run both IPv6 and v4, this support for multiple hardware accelerators and hardware architectures, et cetera, et cetera. So you see how Openshift kind of becomes the center of innovation for the traditional HPC workloads as they being converted into containers, right? Because the features that you would use, or the features that the traditional workloads would use, HPC workloads would use, they are reflected in this list, and they are replicated in the containerized environment. So now that you're familiar with the different adoption phases for containers and HPC, and you understand key technologies and tools that are required, let's look at some of the customers that have already embarked on the journey of moving their workloads to containers. So I want to talk a little bit about the customer references that we have. And of course, I want to start by simply saying that Red Hat has a great legacy in the HPC with, Red Hat Enterprise Linux underpinning top 3 computers in the world. And that's obviously something that we take very seriously and with great pride here at Red Hat. We absolutely love to continue to support these large sites with bare metal operating system environment or containerized environment or the orchestration of the containers as the time progresses. And all of the systems that you see today there running RHEL, and therefore they're all capable of running containers directly on the compute nodes, and they can be used with Kubernetes for orchestrated deployments in the future. But nevertheless, we actually have one customer that has already the top supercomputer, one of the top supercomputers in the world, also running Red Hat Openshift in their infrastructure. And that's the Lawrence Livermore National Laboratory here in the United States. And this is the Department of Energy lab that is focused on supporting the stockpile of nuclear weapons and also safety of that stockpile as well. So they have a very interesting challenge where they were trying to have a standardized interface that will allow them to manage the compute-intensive jobs and also combine the high-performance computing tasks with cloud computing, right? And that's really where they discovered the advantage of the OpenShift, because Red Hat OpenShift provides a common platform for large-scale HPC systems, and also you can move it into the public cloud, and so there's the ability to run this, the same software and same containers in-house or in the public cloud offerings. But really, if you look at the quote there from Bronis Destupinski, their CTO, he's talking about how the overall strategy that the lab has is basically to align the HPC and the cloud technologies can be realized by deploying Red Hat OpenShift, and how we working together to integrate their preferred scheduler framework that's called Flux with the OpenShift to allow them to run these workloads side by side, the HPC workloads and cloud workloads, like I mentioned a couple of slides ago. And we also have another interesting use case, Public Health England, which is basically a UK government agency, right? That is tasked with providing services to the public with the modern interfaces and providing them, services that people can consume on one side, on the forward-facing side, and then on the back end supporting these scientific computing tasks that are needed to track, the spread of diseases and work with, pandemic cases, and like we've recently experienced, and really run the real-time models and simulations on how the disease may spread, while on the front end being able to provide the services to the general public. And really what they're saying here is that the technology that they developed elsewhere before, they had to redevelop it. If they were working for back-end systems or front-end, this was all has to be redone and reconciled. With the adoption of OpenShift, they created essentially a single platform by which they can work and deliver the applications across the both sides of the house, externally facing and internally facing. And from the standpoint of management and maintenance, of course, this was a great improvement, as well as they save costs and were able to do it, for the high performance computing workloads, which require the highest degree of scalability. So that's really helped them to move from the restricted stack of proprietary technologies that they had. They combined about 70 different companies or different applications that were developed by different companies and put it on the open source orchestrated system and take advantage of the ecosystem in general that we have. And this is the real advantage of working with Red Hat. We are the open source company that really collaborates and works in the with the ecosystem in the upstream. Everything that we do is open, and you can, companies that and entities that engage with us not only have the ability to see the code that they paying for, and for the support that they're paying for, but they also have an ability to contribute to that code directly and interact with other contributors within the ecosystem. And based on that, and based on the fact that we're really fully embracing cloud technologies as well as the containerization, I think we have a pretty good position and pretty good way to accommodate any requirements and any requests that are coming from HPC, for instance, to enable the containerization of that vertical. So I would like to thank you for spending your time here with me today and learning about what Red Hat is doing in this space and how we're enabling containerized technologies in HPC. I wish you well. Thank you very much for tuning in, and I hope to see you next time in person.